someone asks a question in chat, I will monitor chat for you and interrupt if that happens.
Just FYI, I have the SPLS Zulip chat open on my computer. So someone who posts a question there, I'll see it. I may struggle to see things in the Zoom chat. Can you see my face? Am I visible?
We cannot see your webcam.
That's so weird because I can. You can. Okay, fine, cool.
Well, some of us cannot. That's really annoying.
I think the problem is it's
there's two of me.
Right.
There's oh, of course, I see. Right, I understand. Hold on. I bet you can see me now.
Yes.
Okay. Oh, this is complicated. Right. Right. We have a bit of a tech fail here, but maybe we can work around it. So I honestly don't know what you can see right. Here I am. Okay. Not the most dignified setup, but it'll do. Okay. I've waffled enough. May I start the talk?
Please go ahead. YouTube link is ready.
Cool. Okay. So as stated, any questions, please post them on the Zulip chat or just butt in. You are extremely welcome to do so. So I'm going to try to give a really simple talk. I'll do my best. I may fail. So let's try to go to the next slide. Thank you all for having me. Thank you very much. And thank you, Andre, for organizing. It's a non-trivial amount of work and we appreciate it. So yeah, some of you may have noticed that I'm quite interested in names. So if you just look, names are everywhere. Here's a partial list just to get us in the mood. You've got pointers, which are names. So the slogan here is name plus extra structure, right? A pointer is a name plus a dereferencing operator. So if I want to know what a pointer points to, I take my pointer name and I say dereference this, and I get a deref. A channel name on the Pi calculus is a name that I can communicate on. So again, it's a name with structure. You've got thread IDs, file handles, and all of that Unix flavored stuff. Meta variables, I would say I would argue, but I have argued, are names plus a capturing substitution. So you can build whole hierarchies of names. I amused myself for several years building hierarchies of increasingly powerful meta variables. There are wires in diagrams, which I know from my work with Geeka, basically Dan Geeka. So you can think of a wire, right? Here, check it out. This is a wire, right? Now, you may not know this, but this end is called A, and this end of the wire is called A, right? So if you have two people who both have A, then they are connected by this wire. It's so simple. Automata up to symmetries, which is non-obvious, but the group in Poland have reinterpreted. I mean, they're working on automata with names, and if these names are subject to symmetries, then you get an automata which is nearly finite, except you may be able to alpha rename essentially names in it. And then there's that old chestnut variable symbols, the X in lambda XX, which can turn into lambda X primed at a moment's notice. And then of course there are variables themselves. You still hear me? Please nod if you can hear me.
We can hear.
Cool, thank you. And then I distinguish variable symbols from variables. A variable is a name plus a substitution action. And I could go on all day, but I won't, because hopefully you've got the point. Please nod if you've got the point. Can I see some nodding, please? This is looking good, thank you. Now, so these things, they need to be programmed on, right? We can't avoid this. At some point, somebody's going to have to write a program that handles names. So there are two packages in Haskell for name management in nominal style, mine and Peter Sellinger's. And there's plenty others, so apologies for anything I've missed out. So what I know of offhand is the Hobbits package, the Bound package by Edward Kmet, which gets a prize for one of the best slogans I've ever seen, making De Bruin. Oh, apologies to De Bruin. I put his I in the wrong place there. Making De Bruin suck less. I worked in the Netherlands for a while and I called it De Bruyne, and everyone looked slightly embarrassed and shuffled their feet and said, actually, it's De Bruin, Jamie. But we'll call it De Bruyne so you can understand us. And then there's the Unbound package. Looking at the times is quite interesting. They're all reasonably recent. Hobbits and Bound were, around about 2010, and the two Nominal packages were around about 2020. It's funny how these things come in bunches. And of course, Connor and others' work in Agda is not in Haskell, but again, it's to do with handling names in various forms. So, there's stuff out there. So a little bit of history. The nominal techniques, the thing, were introduced in my PhD in 2001, so 20 years ago, God help us. There was a programming language. One of the first things we did was to try to integrate these ideas into a programming language. This was FreshML. The slogan was programming with binders made simple. And a determined but unsuccessful attempt was made to integrate these ideas into OCaml. It didn't catch on. There are two reasons for this. One of which I felt comfortable putting into print, which is that, hey, maybe the ideas were ahead of our time, right? It's not that we failed, it's the world failed, yeah. But another reason was just an engineering issue, that every time someone pushed an update to OCaml, Mark Shinwell had to, shadow that update in fresh OCaml, and that's just not sustainable. You can't invent a new programming language just to handle names. You need packages. And certainly I did not understand that at the time because I didn't know anything. And so now it's obvious in retrospect. And it's interesting to note the recent rash of nominal flavored Haskell package. So I don't know. I live in hope that maybe the world is a bit readier for these ideas now than it was 19 years ago. So, okay, so just to sum this slide up, we did try to program with names. It didn't catch on, first of all, because I just don't think the world was ready, and we made some bad, I made some bad engineering decisions, but that's okay, you live and learn. Please nod if you're with me so far, and shake your head if you have a question. I'm looking at, I'm seeing some nodding. Phil, you're looking from side to side. I'm not sure if that's, oh, cool, thank you. Thank you for that. So, the nominal data types package. There's so much to discuss. It's a really interesting package, so let's ignore it. It's too interesting, right? I'd like to talk about everything else. So if the time is right to take a fresh look, pun intended, at names in programming, then what would it take to put principled, practical name handling on the working programmer's workbench? Now, as I'll say in the next slide, having a dead smart Haskell package is not necessarily the best start for this. Right? What about the rest of the world? Now, when you're trying to solve a problem like this, it helps to have some concrete example programs. So I present to you the canonical nominal program. And I put it to you that if you want to study the problem of building a name package, this is a program you do well to start with this one. So let's just take a look at this little tour of Jamie's example program. So in the lambda calculus, this is a function. I've given it a wee type here. So the idea here is this is abstract an atom in an atom. So something in this type would look like lambda a or exists a equals a. So you have some kind of binder and a very simple body. So we input one of these things. We generate a fresh resource, right? Think malloc or Jensen. We just create a new name. And this means concrete. So we unpack the abstraction choosing this concrete A, and then we re-abstract. So this is kind of the identity. We've concreted X at A and then immediately re-abstracted. And we do the same thing here. Now, what's interesting about this is we started off with one binding scope, abstraction scope, and we've ended up with two. Dead simple. Could you either give me a nod or a shake of the head, please?
Can I ask a stupid question instead?
Yes, please, Sam, go for it.
If you take that term and you replace both of your abstractions just with X, do you see what I mean? So
yes, I absolutely do.
Then could you explain how that program would differ from the one you have? Do they have the same meaning, or would they be?
Yes. So it depends what you mean by meaning. The end result, I would say, is the same. The internal operations are different. So I should explain. What we're trying to do is explore what gubbins we would need inside to get this behavior. So if the end result of all this faffing around in this particular case is a simple copy, or looks like a simple copy, that's fine. So we're looking at it from the point of view of being inside a compiler looking out, rather than looking at it from the outside looking in. Does that make sense, Sam? So
semantically, it might be the same thing, but it can be convenient to plug your programs together using these other constructs.
Yes. So your question is a consequence of the computational triviality of this particular example. But that's deliberate, right? It's a bit like saying lambda x dot x applied to 1 is 1. So why not just keep the 1?
So in other words, this is a good example for illustrating the different features of your system, but it's not a useful example.
Not computational. Yes, that's right. Thank you, Sam.
Thanks.
Can I
ask
whether
go ahead.
Whether the point is to not identify these names as being the objects, if you will, in the category, but rather by their identity morphisms, given that each object has its own identity morphism. Is that kind of the point of applying and then abstracting?
I didn't understand that question, but ask me again in 2 slides time if it's still not clear. Would that be okay, Christian?
Sure. Thank you.
Thank you. And Phil, I believe you were speaking.
Yeah, I'm sorry, but I should know this stuff. I'm completely lost as to what you're doing here. So it looks like the type of X is A, abstract over A and then return A. So some kind of identity function.
No. That's, well, it depends on your point of view. The type of X. So this thing here is actually a well-defined, has a well-defined semantics in nominal sets. And I kind of wish I hadn't written it now if it's going to mislead you. But the way to think of this is as in this particular case, think of it as a type of very simple syntax where all you can do is write a lambda term consisting of lambda variable symbol, variable symbol. So it's populated by lambda AA or lambda AB. Those are the only 2 things in this type.
What about lambda CC?
Yeah, that's fine. That's alpha equivalent to lambda AA.
So, except I wouldn't use lambda AA as the type of a variable. I might use I wouldn't even use that, right? I'd use something like for all AA.
Right, I'm sorry, I'm not being clear here. And I don't want to pursue this because I don't want to explain nominal sets to you. So instead of lambda, let's say that this is the type, or a very trivial type of binders, which is populated by simple terms of the form abstract A in A. I am going to carry on. This should become clearer in the rest of the slides.
Should I think of that as the type for all AA?
No, you should not. That's wrong. Thank you for checking. Let me continue. You will see. Just be patient for a minute or 2, Phil, please.
Okay, I'm currently lost. I will let you unloose me.
It's a type of syntactic objects, not functions. It's the type of variable bindings whose body consists of a variable.
Connor's right. Thank you, Connor. I'm telling you, this is the
Thinking
pain
about
of
it
my
as
life.
functions, it will become a lot clearer. Think of it as very syntactic things that happen to involve variable binding.
Is
in an imperative
on you
style.
go.
In an imperative style, we are going to input X, and secretly X is, I'll keep this really simple, abstract A in A. So I know I've written X primed here, but for concreteness, we'll just set X prime to be the name A. So abstract A in A is a first order thing that consists of a binding abstract A in A. And now, I've called this thing A, but fine, we generate a fresh identifier and we concrete X at this fresh identifier. So X primed is the body of this abstraction. So in this case, X primed will also be A, but that's fine. So now I have the body of my abstraction. If I won't use lambda because it might be confusing, so I'll just use first order logic. If you consider for all A equals A, the body of that is A equals A, and we can get A equals A out of it, we can get B equals B out of it, it just depends on what we choose to concrete at. So that's what's happened here. But now, trivially, we're just going to rebind, re-abstract. So if X primed was A, then X1 is abstract A in A, which also happens to be equal to abstract B in B. And X2, we're doing exactly the same thing. We abstract A in A and we get abstract A in A. So it's all pretty trivial, but what's interesting is at the end of it, we have two abstraction scopes. And in the intermediate thing here, we have a, if you like, naked body of X. So we are actually programming on the body of X with a concrete name, which we have chosen fresh here. May I, please nod if I may continue. Phil is nodding slightly reluctantly, but that's, oh, Ohad, you're shaking your head. Go for it, Ohad. How can I help?
So what's the type of this function? Is it a pair of bracket AA? And
hang on one second.
Two...
When you say this function, are you referring to this?
No, the result type. I know what the input type of this function. What's the result type of this function?
The output type will be a pair of abstract A in A and abstract A in A. It's two abstractions.
And the variable that they're abstracting over is going to be considered different, right? Even though it's the same.
Yes,
it's the same atom, but it will be considered different.
It helps to be quite pedantic here. The variable symbol, or even better, the name. Because I haven't said these things are variable.
The name. Yeah, sure. Yeah.
Sure. The names. This is the point, that we start off with one abstraction and we end up with two, which is the key factor. Thank you, Ohad. Okay.
I'm going to ask a different question. You mentioned 5 different Haskell packages at the beginning. Do each of those 5 have an equivalent of this, or just the 2 that are nominal?
I can guarantee you that the 2 Haskell packages, that the 2 nominal packages have exactly this and can write this program.
Mm-hmm.
Actually, I'm not even sure about Peter's. I'm not sure whether I'm not even sure about that. Peter's.
Okay, so this is an example for your package, and we're not sure about the others.
Yeah, the short answer is yes.
Okay.
Yeah, thank you. Thank you. I'm humming and hawing for reasons that aren't really germane to this discussion. So looking at this canonical program, which has already caused us trouble, we know that we input one abstraction. So as Connor observed, this is a syntactic package for this particular example. And so we input one little abstraction and we get 2. And we note that the abstraction here is dynamic in the sense, I'll go to the next slide and you'll see it more clearly. There's a dynamic aspect to this in a sense that we start off with this thing. We generate a fresh name for the body and take this body. And I really want to emphasize here, this is an actual datum that we can now pass around. So it's not wrapped in anything in particular. In my Haskell package, you can wrap it in a monad for safety, the nominal monad, but you don't have to. And then we copy it, and then we You see here, this A has dynamically come into the scope, under the scope of an abstraction. And this A is still free, and then we do it again. So now we have two, we copied A and then we bound it twice. And this may make it even clearer. So here I've just enforced a dynamic property that we always actually choose explicitly fresh names. So there's no garbage. I switched garbage collection off. And we see here how this A primed, when it gets captured, turns into an A double primed. And this A primed here turns into an A triple primed. And this is close to what an inefficient compiler might do internally. So this is what we're trying to do, right? Now, the problem is this is a datum. So how can we abstract? You can't abstract 2 in 2. That doesn't make any sense. If I give you some complicated thing here, I'll cover it up. So now we don't know what this thing is. We don't know that it's A primed. It could be some large structure that contains functions and other stuff. So what does it mean to abstract A primed in this beast? So I will move on. So this slide is making my next point, that although for these particular examples for concreteness, I've taken something very simple, in practice, we don't know what this type here is. It could be anything, and in particular, it could be a function. So we can't induct over it. We don't know what's inside X, and yet we still want to do this kind of thing. So there are 2 ways that I see to do it. One is to assume a permutation action. So this is completely lifted out of the nominal sets playbook. And that's what the nominal Haskell package does. Another is to assume resumable exceptions. Please nod if you've heard of resumable exceptions and shake your head if you haven't. So one person is shaking his head diagonally. I'm not sure. Maybe it's Jein in the German sense. So, so let's just talk about these now. I am of course running out of time, so that's okay. Did say you could interrupt me, so.
Have a long break afterwards, so maybe you can run over a bit.
Thank you. I appreciate that, Andre. So. Here is a nominal rendering of the internals. So this is basically what Peter and my packages do. So we input X, and secretly this is now a pair. So that's compiler internals, right? It's a pair of a name and a body. And Phil, this may begin to answer your direct question here. What do these abstractions look like? They look like pairs internally. We generate a fresh name, and then to form X primed, that is to unpack the abstraction, we apply a permutation of A for A0 in X0. Now, the wonderful thing about permutations is they're really good at commuting with structure. And in particular, permutations act on functions via the conjugation action. So this X now really can be anything and will be fine, will be okay. So this is what we do. And then to reform the abstraction, that's cool. We just generate 2 fresh identifiers. And X1 is just a pair of A1 with permute A1 and A in X prime. Let's just unpack the computation. If we permute A1 and A in permute A and A0, well, A was fresh, so it doesn't occur in X0. So this is just permuting A1 and A0 in X0. So there's this nice simplification that happens. So in other words, the body of X1, I chose my notation poorly. This X0 is a body, this X1 is an abstraction. I apologize, my bad. So X1 is an abstraction by A1 of the body of X with A0 permuted for A1. This has been known for 20 years now. This is standard nominal sets. And we do the same thing for X2. And now we have an explanation of. I can see people staring. Nod if you're okay and I can carry on, or shake your head if I need. Yeah, Ian is. Yeah, I'm seeing some nods. Okay, cool. Then I will move on. Thank you. So a resumable exception is pretty cool, actually. it's an exception. You can raise an exception and then flow of control goes to a handler. The handler does something, adjusts the universe in some way, and then flow of control returns to the site that raised the exception. I like to think of this like a little kid that's trying to do something and then it gets stuck. So what do you do if you're 5 years old and you can't open a bottle of chocolate milk? You invoke the parent exception, right? Dad, I can't open the chocolate milk. So dad comes along, he's the handler, he's been interrupted, comes along, he unscrews the chocolate milk just enough so that those little plastic tabs get broken, and then he gives it back to the child. And now the child can unscrew the cap of the chocolate milk and execution continues. That is a resumable exception. I looked at it in this way. Exceptions always seem to me a bit odd because, that's how real life works. If you encounter a problem, you invoke some help and then you carry on. So that's a resumable exception. So you can poke holes in this program. It's just a sketch, but hopefully it'll give you the idea. So the idea here is now that X consists of a pair still, but this pair is, hey, what is A0? And a body. So we generate a fresh exception, and then X primed, this is supposed to be the body of X, is where we handle A0 as raise A. So that means in X0, in the second component of X, if anybody asks, hey, what is A0? Then this will get redirected to the question, hey, what is A? And then at some point, there might be a top level handler that says, actually A is going to be something, and some concrete thing that you might need to output to the user or pretty print or whatever. So X1 just says, well, if you get a query on the channel A, then continue as A1. So if you run through the flow of control, I don't know if you want me to do this, but I was doing it yesterday just to check. So what will happen here is that if something in X0 invokes A0, then that A0 gets redirected to A, and that A gets redirected to A1. So we have indeed achieved the effect of binding any A0s in X0 to A1, which is what we wanted. Again, I'm seeing. So some people are nodding. Connor was literally scratching his head.
I'm puzzled as to what is A equal fresh exception. Like I understand A is fresh. A fresh is a new name, but A fresh exception is a new.
Yeah, sorry, a new exception name. I couldn't bring myself to just write fresh. I wanted to emphasize that this is now the name of an exception, but morally it's the same as A equals fresh.
Okay.
Thank you. Thank you.
And we have this functionality in standard ML, for instance. You have generative exceptions. You can create as many as you like, and you're guaranteed to get a unique one.
Yes. I don't know whether ML has the resumable exceptions bit, but this generativity, it doesn't. Okay, so next slide. I think.
Well, wait, before we go on, actually, I have a question for
sure.
Sam. So Sam, and all the different forms of handlers that you work with, can this kind of functionality be emulated?
Yeah, we have just the right man in the call. Philip Siekowski has a paper on this, has two papers on this, 2 Popple papers. So I'm sure he can tell Jamie all about this, or how to implement that in his system.
Yeah, let me just unmute and be real quick if you don't mind, Jamie. I looked at the resumable exceptions quickly after we last chatted about them. And yeah, they are basically very particular uses of effect handlers or virtually any of the kinds of control structures that are equivalent to handlers. So appropriately powerful shift 0 and reset would also work, that sort of things.
So
the,
just so
the thing I was trying to say is that specifically in your work though, Philip, you actually have a fresh effect construct, don't you?
Yes, that is true.
Which is the only additional thing on top of maybe standard accounts of effect handlers that you would need in order to do this.
If you really needed these exceptions to be fresh, which for this particular instance, I'm not entirely certain you would need that, but you might, particularly if you really need the freshness in the sense that, you know, with names and all.
Yeah, so for this example, we only ever had one A around. But obviously that's again, that's a product of the triviality. Just so I can place this concretely, Philippe, and thank you for this. Is this something that can be written up in a concrete programming language, or does it, for the moment, just live in papers, please?
It can be. It might not work because the implementation is quite experimental. But okay. Yes, we have an experimental programming language we've developed in Wrocław where you can write these sorts of things.
Okay. Thank you very much. That's excellent. That's wonderful. Can I wrap up with my conclusions? Is that okay?
Please.
Thank you. Okay, so if I can do this. So I propose let's write packages that engineer one or other of the approaches below above in various languages. So what I come to this talk to exhort us to code this stuff up and just get it running. I claim that essentially, if you can do this program, then you can do everything that really matters. And I know that's a simplification, but I think it's a reasonable one. Let me just poke fun of my own Haskell package here. It's subtle. The types, by the way, are really fascinating. Coding this up in Haskell was really educational for me as a researcher. There's papers in this package which I feel guilty for not having written. The documentation, I might add, is comprehensive. I have taken great pains to explain all of the subtleties of this package, but I would question whether that is a compliment, because perhaps this just obfuscates the underlying operational simplicity which we have seen. Perhaps what the world needs is not a subtle Haskell package, but a simple, stupid, better, more accessible package that will work. That's not to say that Haskell package, I mean, it does also work, but you know, you have to read the documentation and understand it and look at the types. And yeah, okay. So I have scratched an itch with this Haskell package, but I am now looking for something short, brutal, and potentially unsafe, maybe written in Perl. You know, it's like I had a really nice girlfriend, and now I'm looking for the bad one. And I feel quite naughty saying this, but I want to simplify, right? So here are the two slogans: names as permutable data and names as resumable exceptions. And I reckon either will work just fine. And if you are a hacker and you'd like to spend a weekend, I mean, this is not particularly complicated stuff, actually. If you fancy spending a weekend coding up one of these approaches in your favorite language, then please be in touch. The end. Thank you for listening.
Thank you, Jamie. Just as before,